Well, I think we can begin. Welcome back, everyone. So we've made it across midterms, but we still have our upcoming exam on this class, which is scheduled for this next Wednesday. So that's probably our biggest announcement of the day. That means next Wednesday, we're not going to have an ordinary class, since it's feasible someone could schedule exam 2 during the ordinary exam time. So we'll only meet today. We're going to be looking into section 3.5. We should finish the notes here today. We're on example 4 of 5 examples total. And then we have kind of a shorter section right after, section 3.6. This was an applied section on exponential growth, exponential decay. Well, any questions at all, folks, before we get started today? Any questions about the upcoming exam 2? Okay, well, just the standard comments about the second exam. Don't forget that you're allowed to have a calculator, such as these two right here for the purpose of the exam, as well as the last page of the exam that's provided is this one right here, the exam 2 formula sheet. And so make sure that when you go to study that, when you are memorizing things, you're aware that these are the formulas that are going to be actually provided on the real second exam. This will just be the very last page. Jamie asks, can we go over number 18 on the practice exam if anyone needs help with it too? I'm sure they do. Thanks for asking about that, Jana. Jamie, I'll be very happy to do so. So that's going to be number 18. And is this on version 1 or version 2 that you're thinking about? Probably version 1. Let me know if I'm wrong on that. So problem number 18 on version 1. Oh, this is kind of a tough one. So glad you mentioned this one right here. So the idea for getting through this question is, let's just jot it over here on the mark on the left, that anytime we say f prime of x, we're referring to the slope of the tangent line. So let me see if I can zoom in on this just a touch more. Okay, that ought to do it. So you have A through D is the ordinary graph. I through IV, 1 through 4, is the graph of the derivatives. So let's put down here. These are the graphs of f prime at x. So that's basically the first thought we want to have for any kind of problem like this one. It is a challenging problem, I'd say, as well. So let's go through this one really carefully. Let me just dismiss that, whatever that is. I'm always surprised at what new pop-ups happen on these things. So starting off, I'd say probably the easiest one to think about is part B right here. So when we look at part B, think in terms of slopes. On this segment right here, the slope is positive for the tangent line. And so we're looking for something that has a positive slope on the left end. Up until you get here, where suddenly slope is negative, then it switches again with a positive slope and bigger than 0. So let's look at the candidates. Well, when m was bigger than 0 here, that automatically excludes this one. That's a negative slope because the graph is below the x-axis. Looking at this almost seems plausible because it starts out positive in this region. But in this region here, we have a negative value. And when we said the slope is greater than 0, that doesn't quite compute on our graph. Greater than 0 slope means the graph should be above the horizontal axis. So this could be the one that we want, but same problem. We have to have a negative slope on this total extent to the left of 0, to the right of 0. And here it starts off negative, but then flips positive. So it looks like the only actual candidate is this one, 4. Let's just double check if it really matches up. Let me get some erasing going. So right where it was m bigger than 0, the derivative had to be above the x-axis. And there it is in that segment. Next, where it said M is less than 0 up there, you have to be below the x-axis. It was below the x-axis in that region. And finally here, M bigger than 0 gives us this one. And that tells us finally that graph 4 is for part A. Any questions at the moment, folks? Thinking in terms of the slopes getting part, oh, it said part A, part B matching up with graph 4. Let me fix that there first. That would be an automatic question. Why do we put part A there? There we go. Any questions, folks? Getting part B to line up with 4? Okay, let's try another one then. This gets easier as we do this because we're thinking about it, getting more familiar with the process, and also by elimination, it becomes easier. So maybe the next easiest graph, let's think of part A, perhaps. What's going on with part A is here, all the way to this region, slope is negative until it hits the horizontal asymptote with the slope m is 0. So we want something that's negative, but then produces a 0 value right there by that tick mark. Let's see. Well, looks like this one does the job. It's below the x-axis until we get here, and then it becomes positive. It should become positive because as we go up this way, the curve is increasing, so the slopes of the tangent line are all positive until we get to this one, the horizontal tangent line. So that horizontal tangent line is going to produce a 0 right here. And now I'm looking at this one. Felt like that could have been the right candidate. But let's see. Yeah, maybe it still is. Sorry, I kind of convinced myself it was the wrong graph, but looking at it further, it looks about right. So from here to here, we have a positive slope. That's what it's doing, positive all the way from here until it goes to a 0 in that location. The 0 that happened here is relative to the horizontal tangent line in this location. That slope is 0, but the derivative is the slope of the tangent line. And so we get another 0 here. Then it starts to come down, meaning the slope is negative. Over here, curve is below the x-axis, so the derivative is negative. So at that point, I'd be convinced. Looks like part 2 is graph A. So 2 down so far. Any questions or comments, folks, with what we've done at the moment? Okay, now that we've been staring at these for a while, maybe, in my opinion, the next easiest one to try sort out might be part D. Let's take a look at this for a moment, and any volunteers from the class to see which of the remaining 2 graphs seem to fit part D. Dan, it says graph number 3. Awesome, let's take a look at that. We start off positive until we get to here, and we hit a 0. Positive until we hit a 0, that looks great. That's negative till we hit another 0, right at the origin. So negative until 0 on the origin, looking great. Positive until another 0 up here. Positive, and there's the other 0. Now it's decreasing the rest of the time, so the graph should be below the axis, and that's what it's doing here. So good call, Dana. This one is part D. Then by elimination, this one should be part C, graph 1. But let's just check it out. It's going to be negative because that's decreasing until it's horizontal. So negative. Then eventually we get a horizontal tangent line, so we get the 0. Then it's positive, but the slope starts out more positive out here. When it's out here, it's getting closer to a horizontal tangent line. So it becomes positive, but then gets back closer to a 0. That's what it's doing, very positive, but then coming closer and closer to a 0 on that graph. So that's how the work goes in putting all these together. Any questions at all, folks, on analyzing these graphs and picking the right one?
Sorry, I have a question.
Yeah.
Is it a coincidence that, like if you count the amount of horizontal asymptotes on the graphs, that's how many times it crosses the x-axis on the derivative graph?
That's an excellent observation and no coincidence at all. So it has a little bit to do with degrees of polynomials and the number of turning points. Say, for example, on part D, it's 1, 2, 3 horizontal tangent lines, but they're also turning points, which means this function is something like y equals negative x power 4 potentially. If you differentiate that, y prime becomes negative 4 x cubed. So 3, or degree 3 means 2 turning points on this one. We said part D landed up with this, and here it is, 1 and 2 turning points. So that's an excellent observation. It doesn't work for every single graph because, say, part B is a weird graph, not a polynomial. Same with part C. But A and D looks like they're honest graphs of polynomial functions. So that observation works for them very well. Other questions about that? Okay, I think this is always good questions to ask right before our upcoming exam. We don't have an official review day, so I always take questions as a mini class review right before the exam. And even if there's lots of questions, I think that's completely fine as well. This is good use of course time. So what I'm going to do with this graphic right here is just put it onto the Moodle website. Let me clear this out. Right up here, I'll call it exam or class review for the exam. Question first? Yeah, I'd be very happy to, Dana. Do you have another problem you'd like to take a look at? Or really anyone from the class? Any problems that folks would like to take a look at from either one of these? Version 1 is new problems, and version 2 is problems out of textbook. Absolutely, let's take a look at that one. So number 20 sounds like there's several ones we could take a look at. I'm glad you're mentioning this because this will be a real problem on the exam. I'm only going to ask this once, and then it'll come back again on the final exam. So the whole purpose of this problem is knowing the definition of the derivative. That means we have to use it to get credit on this problem. Let me just take a quick screenshot on this. Some of the problems are not too bad. Some of them are a little bit more difficult. I'll leave it up to the class. Which one looks like a fun one? Let's say 1 through 4, going in that order. That's a great question. So I would say the one least similar to a real exam question would be this one right here. Not because it's a bad problem, but it would be a really longer computation. This one is an even much longer computation. So I'd say probably that one right there is the most likely candidate. So let's give that one a try. So let's go f of x. Just going to rewrite it so we know which one we're actually calculating. Is x squared minus 2x plus 14. So when we do this kind of problem on the real exam, the kind of fun thing about it is you will know the answer. There's like an answer key to this. We know by the basic differentiation formulas, f prime of x should be 2x minus 2. So that's the answer, but this answer doesn't give us credit because we never use the definition of the derivative. But it's good to just think in those terms because now we know where we're going. To get full credit, we have to go like this. The derivative of f at x is equal to, and let me just make sure we're going to fit this on a page. There we go. So next, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is how we start out on this thing. There's our definition of the derivative. And from here on out, we're just going to write out the results. For this part right here, we usually did this one in the margin because it's a decent computation just in its own right. So let's do that again. I'm just going to move my windows around here a little bit. Okay, so f of x plus h on this problem. There's the result of putting x plus h here and here, in those two positions where x was. So it becomes x plus h squared minus 2x plus h plus 14. Next, working this out, and hang on, let me do just a little bit more with my windows here. Sorry, trying to get this all fit is sometimes a little bit of a challenge. Okay, that looks like there's a little bit better. First thing we'll do is just square out x plus h squared. So when you FOIL that out, it becomes x squared plus 2xh plus h squared. Distributes right here to get negative 2x minus 2h plus 14. So all that just goes right inside here. And by the way, with this kind of problem, a lot of credit is just at this step right here by the red dot and the very next step. Where the red dot is currently, that's the definition of the derivative, which is the major thrust of this problem. And then knowing how to use it is this next step equals limit h goes to 0. In place of f of x plus h, we put in all of that stuff. X squared plus 2xh plus h squared minus 2x minus 2h plus 14. Then go minus. For this f of x, we just put in the original function. So it's going to be minus x squared minus 2x plus 14. All of which is divided by h. So on a real exam, major credit for just writing down the step in yellow and getting to the very next step where we're expanding out f of x plus h and the f of x. At beyond this point, if you made a couple simple mistakes, you probably are not going to lose major credit. Here is really the major work. Still have to finish it off. So any questions, folks, to this stage? Okay, probably the next thing most people would do is distribute that negative into the group. So let's write that all out. We have the limit as h goes to 0, x squared 2xh plus h squared minus 2x minus 2h plus 14. So now we're actually distributing minus x squared plus 2x's minus 14, all of which is divided by h. Those fraction bars are hard to write straight when they get so long. For the next bit, we're canceling. So this x squared with this one. Let's see, we've also got negative 2x, positive 2x, positive 14 with negative 14. The sole survivors is this stuff, and that's negative 2h. Circling them because for me, it's easy to actually miss a little bit. Like, for example, my eyes would potentially read over that step really easy, or that piece. Now it's the limit as h goes to 0. And the numerator, every single surviving term involves h, so we can factor it out, leaving 2x plus h minus 2. Down below is just h, so that's the next cancellation. Next thing we do is take the limit as h goes to 0. That makes that part go to 0. And we're left with just a 2x from here minus 2. Double checking with what we expect from section 3.3, the basic differentiation formulas, and yes, we've got the right answer at that stage. We did it, folks. That's a pretty tough one. Any questions in getting through that problem? Okay, and like you mentioned, there's extra problems here on the actual exam review, but they get more and more challenging as you go throughout the problems. Think of doing it again for g of x or doing it again for capital G of t as just additional practice. They're harder than real exam problems, but in a sense, that's not a bad thing. You wouldn't want to do all the easy problems and then have an exam where the problems suddenly become a notch harder. So it's a little bit the opposite on this exam review. Well, any other questions folks would like to take a look at? Oh, what came through the chat? Paige says, can you do one from number 22? Yeah, I'd be happy to. Thanks for asking about that one. So one from 22 would be, oh, gotcha. So differentiating just to any kind of functions like these. Drop it onto the next page here. It probably doesn't have to be that big. Let's zoom that out. And now let's see. I'd say some of these are more tricky than others for sure. Let's maybe make that bigger, in fact. Say, for example, just on the very, very first problem, if you saw that on a real exam, any volunteers for what the derivative of that function should be? Good call, Jamie. This is just a third root of a number about 2.71. It's all a constant, so this whole thing is 0. So we're at good track on this. On the next one, actually, I want to make the answer be in blue since I think we did that quite a bit on our notes. On this next one right here, if we differentiate this, I'd say this is a great function to differentiate. There's no weird things you have to do with the exponents. It's just go from left to the right. So it's going to be f prime of t equals. First thing that happens is the power 6 moves down, multiplies the 1/2. So 1/2 times 6 would give us a 3. The new power of t is just a 5. Then moving down, the 4 is going to move down and multiply the -3. So that's going to turn into a -12. T to the power of 1 less, so just a t cubed. And then if you differentiate just t, you get +1. So this one is not so bad. Just left to right, differentiate each of the terms. Does that look right to everyone on part B? Okay, awesome. I'd say it starts to get sketchy where we need a little bit more space right here on part C. The first term is not the problem. It's the second and the third term that have more difficulties. For this one, in fact, let's just write down something on the margin. If you see -7 over the 4th root of x cubed, it really can't be differentiated very nicely in that form unless you just have tons and tons of practice with the power rule. I think most people, when they differentiate something like this, they just start working on the exponent first. It turns into -7. The 4th root of x cubed would be x to the power of 3, divide by 4. So the major trick here is the 4 fills out the denominator when we go from radical notation to exponential notation. The next step, -7 stays put. The base x gets promoted up into the numerator, and now it's power -3/4. So that takes care of this one. This one's not so bad, x over x cubed, but what you definitely want to resist the urge of is never use the product rule on something like that. I mean, the product rule isn't even on this exam, so that's a good hint. It's not necessary for these problems. If you do use the product rule, you won't lose points, but the real danger is it's taking a whole lot of additional steps, making the problem much harder than actually intended. So this one, just reduce to 1 over x squared, and then make it x power -2. And the whole function is much, much more easy to differentiate. So any questions, folks, with the preliminary work on the exponents here and here? Okay, let me just rewrite the problem down below. Let's say on part C. With the work we did, y is now equal to x to the power of -2/5 plus x to the power of -2, and then that's a minus, isn't it? -7 x to the power of -3/4. So the reason we did all of that work is this function is horrible to differentiate in that given format. But once we put it into this format right here, it's kind of like what we did in part B. We're just going to go left to right, term by term differentiation. So that's always the strategy. If you see something like this, where things can potentially simplify, always worth the effort of making those simplifications happen. And again, it's not as if the product rule, quotient rule are not good. It's just that it takes way more time to actually maneuver through those rules than it does to just correct the exponents. So back over here, differentiating this function, we'll just call it, say, y prime. Left to right, this is what we get, -2/5. X to the power of, subtract 5/5 on that one to get -7/5. Here, -2 is going to come down over there, so it's going to be a -2. Always subtract 1, so -2 minus 1 gives us a -3. That feels weird because if it was y equals x squared, it would turn into 2x to power 1. But if it's y equals x power -2, power is still dropping as before. It just doesn't feel like it has the same pattern, even though it really does. Final one is -3/4 times 7. That would be a positive 21/4. I multiply the -7 and -3 together. New power of x is subtract 4/4, that's subtracting 1, to get -7/4. Then finally, that satisfies what goes on in part C. Any questions, folks, with that one there? Okay, we were going to do just selected problems off of this one, like Paige suggested, but honestly, I feel like these are all really good, the right kind of questions you want to be ready for the exam. So in case no one's opposed, how about we do all the last two problems on here? Is that all right with folks? Okay, let's keep on going. Oh, I do have some chats. Great, sounds like everyone's on board. So let's finish off these last two. So here's our part D. Probably just want to do this on the next page, maybe. And so I don't forget, let me grab part E right away as well. Okay, well, first thing that happens on this one is, again, you could use product rule, but it's much easier to just FOIL this one out and go from there. So I'm going to make that our first step. And in fact, it wouldn't even be appropriate for me to use the product rule because it's an exam 2 review, and exam 2 ends in section 3.3 anyway. So h of x is going to be equal to, I'm going to FOIL this way, and then take that result and distribute -3 inside. So it's -3 multiplying. FOILing this out, I visualize it with 2x distributing into the group to the right first to get 4x squared plus 2x. Next, distribute your -3 in, minus 6x minus 3. People who are really good at mental arithmetic and just FOILing things a lot often combine those middle two terms. I do sometimes, but if I'm being careful, I just take the additional step. Oh, don't know how I'm calling that thing up. There we go. So now it's -3, multiplying 4x squared, 2x minus 6x for -4x, minus 3. Last thing is to distribute the -3 in to get -12x squared plus 12x plus 9. Double checking. I think we've got the right thing. Does that look right to folks? Okay, well, the way it stands, this looks like part B once again. We're just going to go left to right differentiation. Awesome, thanks, Alejandra. So first, 2 is going to multiply the coefficient -12 to get us -24. That x is now to power 1, so we skip writing in the power. The power here is a 1. We visualize it, even though we don't write it. So 1 multiplies the 12. We get plus 12. The new power of x would go to a 0, so that's why it's gone on the next step. And because this is a constant, we don't even do anything with it. It goes to 0 upon differentiation. And writing in plus 0 is just making us take an additional step to simplify, so we just usually leave it right there in that format. So that's how part D goes. And unusual about this, once again, is the algebra took more steps just actually FOILing this all out and distributing than the derivative did. Well, this is going to be our last one from question number 23. And same idea with this thing. You can use the quotient rule on this one, but I promise the quotient rule on that thing is much worse than using the product rule on even this one, in my opinion. So the best step is just to say, if you're dividing by just a 5x squared, that's one term, you can rewrite this as 15x squared divided by 5x squared minus 5x divided by 5x squared plus 3 divided by 5x squared. So all I'm doing here is dividing everything in the numerator by the denominator. On the first term, we're going to get that that's equal to 3. Here, the 5's cancel, so it's x divided by x squared, so minus 1 over x after simplifying. Here, the coefficients, or the constants, are 3/5. X power negative 2 in the denominator, we can move up to, excuse me, I said that weird. X to the power of a positive 2 in the denominator, we can move up to x to the power of negative 2. I should have done that to this middle term. Oh, I think I just totally forgot. I canceled and just moved on. So let me take one more step and write this as 3 minus 1 over x becomes x power negative 1 plus 3/5 x to the power negative 2. Last thing we do is just completely differentiate this. You could call it y prime, but just to get used to the notation, I'll go dy dx in Leibniz notation. Here, this would go to a 0 as a constant. Over here, negative 1 multiplies negative 1 in front, so it's just a positive x. I'll just write x here to the power now negative 2. On this one, negative 2 multiplies just the numerator 3 to make it a negative 6/5. And now x is to the power negative 3. So that's how this one here goes out, or gets calculated. Any questions at all, folks, with the conclusion here? Okay, so I think that's the last question so far. I'm happy to take more questions as they come. Dana said, on version 1, will we have questions like the first few from chapter 2.5, like question 14? Let me take another look at that. Oh yeah, continuity is a section that feels like it's, yeah, I'd say question number 14 is a pretty standard question on these kinds of exams. So I guess we could give these a try next. And while we're looking at that one and thinking about continuity, let me see if we can pull up something else here as well. Let's see. I think we said somewhere on the actual notes in section 2.5, I know this was weeks ago, this is before exam 1, we said a problem like this one can potentially be on either exam 2 on Wednesday or potentially the final exam. So with that in mind, let's take this along with us as well. I think that'd be a good additional question. All right, I'll put it on the document so I don't forget it's there. And as far as this question goes, they're basically all kind of the same. So I'll pick this one right here and let me know if you want to try out a different one as well. The fun thing about these types of limits is if it's asking you to use continuity, you have to remember that continuity is just a different way of saying direct substitution. So for example, if we do this limit right here, limit as x tends to 1 of the natural logarithm of all that stuff, the first thing we wonder about is our function actually continuous at a positive 1? It might not be. If they're saying use continuity, then it should be, but we should double check as well. Get a 2 in the denominator. So that looks like it is continuous there. If this was a negative 1, however, the problem is flawed. It's not continuity. It'll mean it's not continuous. That's because with a negative 1, we'd be dividing by 0 here due to the 1 plus x in the denominator. So in total, the way this one goes is it's going to be equal to, we're dropping the limit at the very first step because we're using just direct substitution. X equals 1 gets plugged in here and here. So we get all together 5 minus 1 squared, 1 plus 1, so this is 4 halves, for a value of 2 altogether. Well, any questions, folks, with number 14? Or any additional problems on here you'd like to see done? Okay. Oh, good call. I was focusing on just the fraction in the middle. I forgot the natural logarithm. If this was a real exam question, let's say out of 5 points, I feel like that would be a really hard one to really decide on, but probably a -2 on there. That's a pretty major observation. Thanks for spotting that, Jamie. So correcting my work after the fact, let me see what I can do here. We'll put a little red pen here to make that on the official record. This is equal to the natural logarithm of all of that stuff, which then turns into the natural logarithm of 4 halves becoming natural logarithm of 2. Yeah, I'd be very happy to. So one with negative e. So maybe not on this list, or you're referring to maybe this one right here by the red dot. Awesome. Let's give this one a try next. So on here, we have t going to 0. T going to 0 is only going to affect that part of the function. So we get altogether that this is 17 divided by 9 minus e to the power of negative 1.4 times 0. So 0 came from right here where t was heading towards. Now over here in this location, a little bit more algebra than I'd say on the problem that I did right up here. This one becomes 17 divided by 9 minus e to the power of 0 altogether, because the exponent is negative 1.4 times 0. Next thing we have is an exponent law, which goes like this. A to the power of 0 is 1, provided a itself is non-zero. So e is not 0, it's about 2.71. So e to the power of 0 itself becomes a 1. That means this is now 17 divided by 9 minus 1. Then simplifying denominator, we have 17 divided by 8. So I'd say the worst thing about this problem, in all honesty, was it just took a little bit more steps. We had to use some exponent laws with that power 0 right there to get to the end conclusion. Worst thing about this problem is forgetting that there's an actual natural logarithm in front of the actual rational function. But any questions, folks, on getting through either one of those? Yep, absolutely. Thanks for asking about that one, Paige. Okay, let's maybe take a look at this next one, because I feel like this question right here is always really, really esoteric. Continuity is easy to see when you're thinking in these terms, or drawing a graph. There's no holes in your graph. In these terms, you're just using direct substitution. So we just literally plugged a 0 right where the red dot is and cranked out the limit in that way. But now in problem number 11, this one is a tricky question. The way to think about this one is its whole purpose is a reminder that in calculus, every single interesting concept seems to come in some way from a limit. That's the reason why on this problem, we're using the definition of the derivative. It's just a reminder that even when we have fancy differentiation formulas like this one, every single one of those formulas came from this number. And same idea here. Continuity is one of the major ideas in calculus, and it is also defined in terms of the limit. So let's read the problem carefully. Write an equation, that means there's got to be equality somewhere, that expresses the fact that f is continuous at the number 4. So if we're continuous at the number 4, the one thing that this means right out of the gate is we're going to write the limit as x tends towards 4. So we've just have to write that bit right there for this bit of information. The function goes inside f of x. And I'm just going to rearrange my equality, bring it a little bit closer. And for some reason, I was going to write really big. So final thing to write is something now goes on the right-hand side. Anyone recall what it should be? There is a bit of a hint on this one. The hint is, it's kind of like what we see right here. Think of this whole thing as f of x, much like our f of x down below here. Think of this as an x or t heading towards 0. I guess this is a t, so that should be an f of t. Let me fix that right here. T is always kind of awkward variables, tragically. There we go. So we're heading towards 0 on this one. This whole thing is f of t. Then this part turns into f of 0. The whole function was f of t, and so plugging in 0 there, the only location t occurred in gives us f of 0. Same thing over here. If you're heading towards 4 in the limit, and you have a function f of x, we just write f of 4. And either way we think about this, this is always direct substitution. The arrow in orange is not required for the full solution, just extra information on the notes. Well, any questions, folks, with either of those concepts in continuity? Or any of the questions folks would like to take a look at? I'm happy to look at more folks would be see any that there looks like it would be helpful.
Could we maybe do number 23?
23, absolutely. Thanks for asking about that one. So I'm on the wrong document. Forgot they're over here. So 23, let's see what we're getting into. Oh, really glad you asked about that one. So this is a tangent line equation. You can pretty much expect a problem like that one to be on exam 2, maybe exam 3, but definitely the final exam. And I think this one is tricky. There's a really good reason why it's tricky. So first, let me explain. This is a tricky question because the very first time we see that question, we were all the way back here. To find, which means the very first we used that for here, red dot. That's the derivative once again. That's why the problem looks really awful. That's a big computation just to get a tangent to come through. But the promise with these problems on really exam, the only time you ever have to use the definition of the derivative is if the instructions look like this. Explicitly have to use the definition that hold the rest of the equation. So now current one, taking a look at problem number 23, nowhere does it say use the definition of the derivative. And so idea to back to the derivative on this one, use our differentiation formulas. So step 1, we need to find the derivative of that function there. Usually these are not crazy derivatives. This one is more just what a tangent is and how to calculate it. So usually the derivative is fast right here. Let's call it dy dx. Going left to right, x power 4 turns into 4 x cubed. On this next one, 4 and x. Any one. Okay, step 2. If we're going to get to the 10 slope, that's exactly what we're going to say. Let's go. The slope is going to be the derivative versus pi. Excuse me, the derivative to x. We say that. X equals. Here's the first drama in the problem. Is x 1 or is definitely comes from the point, but anyone see what value we need to use? Good call, Peach. We're always using the first coordinates. Grab that value 1 right. So when x is arrow, well, we put d right here. Only different plugging in 1 and that whole derivative. We'll read it plus 4 minus, so 4, which exactly. Any questions of you? Okay, 3, so I use y1 is x minus x1. The x1 come from other plugging information. So this will become minus from y1 2. I might also because that's probably the step there. Getting the slope tangent line is battling. So more than half credit to step. So 7 times we solve for y. So let's just so we'll get y is 2 equals 7x after adding 2 sides. So that would be our whole tangent line equation. It's always good to look back what we did in the past. And again, I make a big deal out of this one because it is tricky We never break one, but we didn't have a differentiation like we did in step 2 when we were way back there. Well, any questions on doing any other so far? That meant, let me pull it up again. Oh, we'll scroll up here. 20. Now, I was about to, because those where it's not meant to hard problem its own. What makes it hard is notation there. So copy that. Kind of good timing too. It's doing number 24. Hang on, let me get my stuff to work out. There we go. Doing problem number 24 after number 23 is pretty helpful because this right here is very similar to what we did right there. This is just a way to express, I want to take the derivative, dy dx, and plug 1 inside whatever the formula is for that derivative. Down here, this is a new way to express. We want now the second derivative of y, and then plug in 1 after we get that result. So let's try that out. The phi involves an exponential function. So we go to calculate either y prime, which is dy dx. Totally up to you, notation you want to use. It doesn't have to be this way. Y prime is d2y dx. So for that function there, let's sticking to Leibniz notation. Let's get dy dx equals the derivative of 2 e to the dx. That's a constant multiplying an exponential function. So we just get 2 e to the dx back, since the derivative of e to the x is itself. Over here, we do have a change. We use the power rule, positive 2 multiplied by negative 5. Giving us negative 10x. So that's our step 1. Next step, we just differentiate again. So if we're trying to get to the second derivative, d2y dx2, we operate on the first one and just differentiate again. So here's how it goes. d2y is just saying we're taking the second derivative of the same function y. dx says we're differentiating with respect to x both times. But if we differentiate 2 to e to the x once, then we get the same result as we did the first time. So differentiate times you differentiate that function, it survives in that same exact format. This one always changes though. The derivative of negative 10x is just negative 10. And here's where we're going to now do the evaluation. But any questions at all, folks, to get to that step, the second derivative? Okay, so finally, calculating this thing out looks like this. d2y dx evaluated when the x is 1 means we take this whole thing, plug 1 in for x. So it's 2 e to the power of 1 minus 10. But e is just a number, and e to the 1 is just 2e minus. That's where the problem with you have calculators that you're allowed on it. So some people put this calculator, but it's totally up to do that. I'm happy back now. Any questions for me? And I guess same question as before. Any other additional questions folks would like to take a look at? Okay. Well, this has been we'll do this for our exam as well as for the final exam as well. However, I'll try to add more structure in some more new additional problems. It'll still be kind of like this. We can go all over the map, just depending on what problems people would like to take a look at. So let me save this here. These notes, the exam 2 review notes, are going to end up right before the exam form of the sheet. In fact, I'll do that after. Actually, probably not a good use of exam. You watching me convert the file and upload it here. But that's where it's going to end up right after. And with the time we take a look. I think we have a little bit of time. What we'll do next is take a look at section 3.5 chain rule. But I'm not going to go too far, so if it makes sense to end early, we'll end a little bit early. For example, we're not going to open up section 3.6 on exponential decay. That definitely wouldn't make sense. We'll be taking a look at that after the exam. Yeah, I'd be very happy to. Let's take a look at question 21 next. Open. Again, I should have closed that document. Sorry about that. I guess it's fast to open. And question 21 goes, the graph of f is given reasons the number at which f is not differentiable. I should mention, just full disclosure on this one, this is content that we didn't actually make it to when we were in section 2.2. So this one would not be on the real exam. Let's talk about this one a little bit. We're trying to find where f is not differentiable. And the idea behind this is that differentiability is a stronger condition than even continuity. So if your function not column right here at x equals 1, f is not continuous. That's the continuity that comes on the upper exam because of continuity. And so f not differentiable. There. So that gives us one point where it's not differentiable, but there are two others. So the idea with differentiability is it's a type of smoothness condition on your function itself. If your function is differentiable, you should curve looking like this. The segment right here where the red is. Differentiable curve considered curves certain continuity. The thing they can't have is a hard corner that would appropriate real differentiable functions. It looks like a sharp corner like that they're circled, and right here is a major problem. And think of it from this point of view. Imagine this is a roller coaster ride. You're just looking at side view of it. And you're this end, right? Because we expect and to right, but you're right. Everyone's going to get it in connection or some other emergency. Can't go straight. So actually cannot have anything like that. A nice roller coaster ride. So let's say x equals 2 positive f differentiable. Sorry, I forgot how to spell differentiable. And my Control Z delete stuff out of order. That's really weird on this computer. With what's going on with that graph there. Sorry for accidentally including it on the exam 2 review. But you know what? I'm glad we asked about this. Any other questions about this one here, folks? Okay, and just more double. Any other folks, Gus? No, you wouldn't have to say that for this problem here. The problem actually said state the type of discontinuity. If I had it directly along those lines for exam problems, let's just double check. Take a double look at that. Let's see. Yeah, that'd be like question number 12 for example. The numbers at which f is discontinuous and explain why. We would say at -1, infinite discontinuity. And negative, we'll say a jump discontinuity. And then another jump discontinuity at 1. But I'd have to tell you explicitly. Let's see here. Explain why it's discontinuous for you to have to give that kind of response. Other questions at the moment? Yep. And thanks, Herb. I think on our first exam one review, we didn't have as, I think, launched right back into the lecture. It was probably like a 30-minute review. I really appreciate and record time. Before, say questions on this. Thing. When I was I asked every single time from two. As again, I'm going to try to all my same language. Any other? Okay, well, we're pretty hard on. If you work, yes, so come up with that. But also, I'm glad to hear. Really see what were difficult, just seemed a bit vague. So far, got to Sorry class. I have a very awesome glad Dana. This is the first happened with me with mandatory meetings I attend with looking at these minutes I'm putting in for interruption office hours. My next we're seeing is the example portion. I can give a different offer with this one here, this interruption. The thing is that we're not holding class anyway. Wednesday, October 6th. So what do on Wednesday? I'm going to make a formal announcement that watch everybody. I intend to hold office hours still on Wednesday. They'll just go from 2 to 3 o'clock, the time we've been studying on this exam here. So I'll record them as well so that people, if they decide they're helpful, that they can come back to those notes there. Again, office hours that go from 3:30 to 4:30, the ones we will have today are canceled on Wednesday. We'll just do 2 to 3 o'clock on that day there. So if you have additional questions, don't hesitate to pop back in. Any questions whatsoever, folks, about the exam review? Okay, well, that's so far here in 5. Not what we've been about. So root 9x minus 8. We're going to find exactly as before. Same sequence as could be in exam 3. This problem by just doing a little bit of additional work on the function y. And we have a major problem already. This for an example. We always made the root worked on the x sign, and you're taking the square root, right? This says 9x minus 8 to the x. We can use the power here. And now we can also, that's a function differential. The one's referred to as the second, and that's the function referred to the inner function. We're working out these notes. Derivative dyx looks like this. We want to change this to line, and our inner function, our inner function is green. Shaded in that form is going to differentiate that. So subtract 2 over 2 at negative 1/2. And because it's a chain rule, we have to make a little multiple. And this placeholder, the inner function, both slots. So next we don't, we're just exactly turning into 1/2. So here's our times 9. Just come up with the derivative. Next for n equals when x coordinates to chart, we're going to plug to 1/2 times 9, 1, 9 minus 1 times 9. So altogether, the slope is 9/2. The last step of just putting it all together. Scroll down better. Right, this 1 right here. This slope m, 1 on the left equals times x minus 1 on the right. So we have y minus 1 here to a 2 over 2. Now 9/2 x minus 9/2. We'll get 9/2 x minus 7. Well, we did it, folks. That's the conclusion of the problem, where we'd see problems just like if you leave this homework section till after you take exam 2. I think that would make a lot of sense. Focus on sections 2.5 to 3.3. Then after exam 2, start looking into the homework for sections 3.4 and 3.5. And that would make a lot of sense for where we're at in the week right now. Well, for this example 2, I'd say this is a good stopping point for us on the notes. We have an applied problem down here, but this is not a problem that's actually in the homework for this section. This was more if we had additional time. Here's another problem where the chain rule could come into play in this sort of setting. If you're curious about this problem, let me know. I'll be very happy to solve it and show you how it goes. But otherwise, we're going to think of this as our last problem for the notes here on this section. Well, any last questions, folks, before we call it a day a little bit earlier today?
So does the exam have to be taken on Wednesday, or can we take it on Thursday if it's more convenient?
Thursday's okay, absolutely.
Okay.
Yeah, the thing that's really, really tricky about an online class like this one is, even though our exam is officially on Wednesday, because of the testing center having to work with everyone's schedules, and schedules are not always easy for this kind of thing, it's actually open to be scheduled anywhere between the 14th, so some people maybe have taken it early already, all the way through the 18th. So any one of those days, you're welcome to schedule your exam on, and that'd be totally fine. So Wednesday is like the official day. That's why we don't have an ordinary class on that day, but the whole week is open for that. Thanks for asking about that, by the way. Other questions at the moment? Okay, well, this will be our stopping point for today's class. I still have office hours today as usual, 3:30 to 4:30. But again, I do have an office hours interruption on Wednesday, so we'll just move up the office hours on that day.
I guess my only other question is if we can push off the 3.4 homework until we're done with the test, if is there any way we could maybe get an extension on that?
Oh, yeah,
I think
absolutely.
I think it was due today, and I was just wondering if maybe we could have it due like on Wednesday or Friday or something.
Extensions just from the homework system itself, or would it be helpful just to show that?
I know how, I just thought this was faster.
Yeah, I think that'd be honestly, probably just a good idea generally. So yeah, let me take a
Okay.
look. 3, 4. Oh yeah, that was supposed to be due today. I'll take a quick note here. Move few days out. Yeah, I'll be happy to do that. Thanks for asking about that, Cameron.
Yeah, I don't know if anybody else is having issues, but my Cengage isn't showing like my current course, so I might have to figure that out, but
Oh, weird. Let me know if that keeps on going on.
I will. Thank you.
Yep, absolutely. Any other questions at the moment, folks, before we call it a day? Okay, well, it's been a fun class, folks. Again, I really appreciate the energy during the review. That was really great. If you have any questions, whether it's during the office hours or sending them through email, I'll be happy to help out. But have a great rest of the week, and I'll see you all next week.